This is the second hour exam review for Chemistry 122, spring of 2021. I'm reviewing those problems that were most frequently missed on the exam. First problem I'd like to cover is problem number 1. If tripling the concentration of a reactant A multiplies by the initial rate of the reaction by 9, the reaction is what order in A? So if we're doing an experiment where we have the rate of the reaction, we have the concentration of A. Let's say in this first set of conditions, the rate is 1. The concentration of A is 0.1. Then we do a second experiment. The rate of reaction, the rate of reaction is one. The second experiment, the concentration is 0.3. And the rate of the reaction goes up to 9. What is the order of reaction with respect to A? Well, this means that A goes to products. How do we write the rate expression for this reaction? Rate is equal to some rate constant K times the concentration of A raised to some exponent X. Well, if we're comparing the rate of the reaction for the second one versus the rate of the reaction for the first reaction, rate constant K times the concentration of A to the X. Well, in the rate of the second reaction, that rate is 9. The rate in the first direction is 1. K's are constant. The only thing that changed from the second experiment to the first is the concentration of A. A in the second experiment is 0.3. A in the first experiment is 0.1. So we have 9 over 1 is equal to 0.3 to the x divided by 0.1 to the x. Properties of exponents is that we can factor this into a single problem. 9 over 1 is equal to 0.3 divided by 0.1 raised to the x. Well, this is 9. 0.3 divided by 0.1 is 3 raised to the x. 3 raised to the what power is 9. X here is equal to 2. So the order of reactant with respect to A is that it is second order. Number 2, given the following reaction, A plus B goes to C plus D. The rate of the reaction is equal to some rate constant K times the concentration of A times the concentration of B. So we're looking right here. I don't know if you can see that dot or not. Nope. Okay. The rate of the reaction is equal to some rate constant K times the concentration of reactants raised to their coefficients. So here the rate is equal to K times A to the first power. Because we don't see a number there, we assume that the power is 1. No number here. We assume that the rate exponent here is 1. Since the exponent for A is 1, the exponent for B is 1, the overall order of the reaction is the value for the exponent of A plus the value for the exponent of B. Since they're both 1, 1 and 1 is 2, so the overall order of this reaction is second order. Number 13. Given the following information. 2 carbon monoxides plus O2 gas gives us 2 carbon dioxides. The equilibrium constant for that reaction is 5.8 times 10 to the 18th at 25 degrees C. So we know what this reaction looks like. What did we do to this to get it to look like this? We took this on this side and put those two on that side. So we inverted the reaction. What was a reactant becomes product. What was a product now becomes the reactant. So if written this way, K sub C is equal to concentration of CO2 squared over the concentration of CO squared times the concentration of O2 for this first reaction. 1. K sub C1. This is K sub C1. Well, since we've flipped this reaction, CO2 now is no longer a reactant, it's a product. So let's call this K sub C2. CO and O2 are now not on the bottom, they're on the top. And CO2 is on the bottom. This is to the 1/2. Each of these is to the 1. Well, we've already said we've inverted this. So K sub C1 and expressing this, these are inversions of one another. We've just flipped these things. Here, reactants become products, products become reactants. So we've inverted the reaction, but what also have we done? Here, it is 2 CO2. Here, it is 2 CO. We've cut these things in half. So not only have we multiplied everything through by a factor of 1/2, because 1 CO2 is 1/2 of 2 CO2. If we have the expression for what it looks like in these terms, it's half as much of that. So K sub C2 is equal to K sub C over 1 over 5.8 times 10 to the 8, 5.0 times 10 to the 18th raised to the 1/2 power. So we inverted this. This becomes 1 over that. K sub C is 1 over this. We've also changed the coefficients in front of everything. We've cut everything in half. So if we cut this in half, this is 1. If we cut this in half, that is 1. If we cut this in half, that's 1/2. So the relationship between K sub C2 is this inverted taken to the 1/2 power. You see number 18. Of these bases, which is the strongest? Hint, Ka times Kb is 1.0 times 10 to the minus 14th. Ka is the acid strength. So essentially, we're looking for the largest value of Kb for each one of these guys. So we're looking for the largest numerical value. That value that has the largest Kb value will be the strongest base. We don't have Kb directly, but we have Ka. Ka times Kb is equal to 1.0 times 10 to the minus 14. So for number A, K sub B is 1.0 times 10 to the minus 14th divided by 7.2 times 10 to the minus 4th. Kb for the second one is 1.0 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5. Kb for this third one, 1.0 times 10 to the minus 14th divided by 4.4 times 10 to the minus 7th. This one is Kb is 1.0 times 10 to the minus 14th divided by 4.7 times 10 to the minus 11th. Kb for ammonia is 1.0 times 10 to the minus 14th divided by 5.6 times 10 to the minus 10th. Real quick way to solve these things is when you are dividing values that have exponents times 10 to the minus whatever that is, you subtract this bottom number from the top number. So 14 minus a minus 4 gets us a value of something times 10 to the minus 10th. Kb, again, how we handle exponents, numbers with exponents, we subtract when we're dividing them, we subtract the bottom number from the top. So a 14 minus a minus 5 or minus 14 plus 5 is times 10 to the minus 9th. This guy, again, we're looking at 1.0 times 10 to the minus 14th divided by 4.4 times 10 to the minus 7th. Again, subtract this bottom number from the top. Minus 14 minus a minus 7 is some value times 10 to the minus 7th. Here, for carbonate anion, 1.0 times 10 to the minus 14th divided by 4.7 times 10 to the minus 11th, minus 14 minus a minus 11 or minus 14 plus 11 is equal to some value times 10 to the minus 3. The Kb for ammonia is 1.0 times 10 to the minus 14th divided by 5.6 times 10 to the minus 10th. Again, you subtract 14 minus a minus 10 minus 14 plus 10, you get some value times 10 to the minus 4. So of these values, the carbonate anion is the strongest base of all of these. Number 20, the magnitude, the size, how big is the value of Kw? 1.0 times 10 to the minus 14th, that's really, 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 really small. It means that Kw is the ionization strength of water. Here, this water is acting as a base. This water molecule is acting as an acid. This donates an H plus. The H2O picks it up, giving us H3O plus and OH minus. The Kw says, how far to the right does this go? It only goes to 1.0 times 10 to the minus 14th. That's incredibly small. This ionization does not go very far to the right. Yes, it does occur to some very small extent, but again, it's a very small extent. Therefore, we say water autoionizes to only a very small extent. That's number 20, and the last one, number 24. The Ka of hypochlorous acid is 3 times 10 to the minus 8 at 25 degrees C. What is the percent ionization of hypochlorous acid in a 0.15 molar aqueous solution of hypochlorous acid at 25 degrees C? Gives you a hint. Percent ionization is equal to the H plus concentration at equilibrium divided by our initial acid concentration. Well, let's write out the reaction. Here we have perchloric acid, hypochlorous acid, ionizing to give you the OH plus and the ClO minus. The Ka, the acid strength of this reaction is 3.0 times 10 to the minus 8th. For this reaction, the Ka value is equal to the H plus concentration, i.e., H plus concentration at equilibrium times ClO minus divided by HClO. Well, in this reaction, we have our initial conditions. Since this is a weak acid, this doesn't go all the way to the right, but it goes in an equilibrium fashion. We have our initial HClO concentration, 0.015. Initially, 0 and 0, before we put the HClO in water. 0 H plus, 0 ClO minus. As this goes to equilibrium, some of this goes to the right. How much? We don't know. Therefore, the change is X. As this reaction goes to the right, it produces H plus and ClO minus. How much H plus? Well, since this is in a 1-to-1 mole ratio, as many moles of HClO decompose or ionize, we produce X number of moles of H plus and X number of moles of ClO minus. So this is X, and that is X. Since HClO is a reactant, over time its concentration is going to decrease. So the change there is a minus X. How much H plus do we produce? So we're producing it, we're making it. Initially, we're starting at 0. We make plus X. Since H plus and ClO minus are produced on a 1-to-1 mole ratio, this is also plus X. Such that at equilibrium, you have 0.015 minus X plus X plus X. Remember, we're asked for the percent ionization. Percent ionization is equal to our H plus concentration at equilibrium divided by our HA concentration initially. Put in the value for H plus, that is X. Put in the value for our hypochlorous anion, that is X. Concentration of our HClO at equilibrium, 0.015 minus X. The values here are equal to, if we were to get the X term, they're equal to 3.0 times 10 to the minus 8th. So 3.0 times 10 to the minus 8th is equal to X squared over 0.015 minus X. If we had to solve the problem from here, we would have to use the quadratic equation. That's a math problem. This is not math, this is chemistry. So we can neglect the X term. We're saying that the degree, how far our acid ionizes, the amount that it ionizes is so small that the change that is made to the concentration of our acid is negligible. So it's 0.015 minus 0.00000 something that is so small compared to this that this is essentially still 0.015. We can neglect the x. That simplifies to 3.0 times 10 to the minus 8th times 0.015 is equal to x squared. So 3.0 times 10 to the minus 8th times 0.015 is equal to x squared. So multiplying these together, I get 4.5 times 10 to the minus 10th is equal to x squared. Take the square root of that, I get x is equal to 2.12 times 10 to the minus 5th. What is x equal to? X is equal to our concentration of our H plus when it's reached equilibrium. Remember, our initial concentration was 0.015. So the percent ionization is our H plus concentration at equilibrium. So 2.12 times 10 to the minus 5 divided by 0.015 times 100. I get 0.14%. So the answer here is D. Again, these were the problems that were most commonly missed on the exam. If you have any question about a problem that I worked here, or I didn't cover the problem that you had a question about, please make an appointment to come to my office during my office hours. My office hours are posted on the class syllabus. Have a good break. See you guys on Monday the 12th.